I'm going to talk about calibration improvements since cycle 1 or cycle 1/commissioning. I don't have as fancy an overview of the instrument as we saw for NIRSpec, partially because we're a simpler instrument, but mostly because it's all on JDocs. And if you're interested, you can go there and fairly quickly see the characteristics of NIRISS, but we are primarily a spectroscopic instrument, and we have 4 observing modes. We have some imaging capability from 0.9 to 4.8 microns, which overlaps with NIRCam. NIRCam is generally going to be the preferred imaging instrument, although there are a few use cases where it may be better to use NIRISS, but generally you would use NIRCam. We have a wide field spectroscopy mode, which gives us a low resolution spectra of objects in the field from about 0.8 to 2.2 microns with not quite total coverage. Then we have 2 modes that are optimized for exoplanet observations. The single object spectroscopy mode, which gives you a spectrum in one shot from 0.6 to 2.8 microns for bright targets. It's optimized for exoplanet transit observations. And we have an aperture mask interferometry imaging mode intended for primarily exoplanet direct images at small angular separations from 0.07 to 0.33 arc seconds. Separation in the longer wavelength part of our range from 2.7 to 4.8 microns. Something to note, which is sort of implicit in what other people have presented for other instruments, is explicitly when we were in calibration in commissioning, we were doing a minimum calibration. And the same was true with the pipeline we had at that time 4 years ago, in some sense, a minimum pipeline, enough to get a reasonable reduction, but not certainly the best possible reduction for these different modes, and how good it was depended on, in part, how complex the mode might be. And it was always intended from the start in the planning that we would then need a period of some years, presumably, to revise and extend the calibration and produce better quality data products, as well as making improvements in the pipeline. And we're still doing that now in cycle 4, to a greater or lesser degree, depending on which mode we're talking about or which instrument. And we're going to continue this in cycle 5 and probably beyond. So just to orient people. So of course your data products from NIRISS or the other instruments keeps improving with time. But this was something that we knew was going to be happening when we launched JWST. So I'm going to talk about calibration improvements in the sort of high-level sense for each of these modes and also the general ones. And I am also thinking about pipeline improvements, because we don't just improve our calibration in terms of the reference files, but also in terms of the algorithms that we have in the pipeline, which depend on these measurements, and all of these things together improve our data products. I'll start with a brief talk about some general calibration improvements, which are detector level effects that we've characterized since we started 4 years ago. These apply, therefore, to every mode of our instrument. We've got one of our F noise removal improvements. This is a noise in the detectors, in the channels that are reading out, which the eye picks up and which people find annoying. It is not as big a deal for the science measurements, although sometimes it has an impact. We spend a lot of time on that. We spend a lot of time on detection of and correction for cosmic ray hits, which are a fact of our existence at L2, happening all the time. some of which are large so-called snowball events, which I'll show you an example of in a few minutes, which are particularly difficult to deal with. We have characterized a charge migration effect in our detector, which we did not realize was happening before launch, where you could have a photon producing an electron on a given pixel, but if you have a voltage contrast between that pixel and the one immediately beside it, the electron can actually move to a different pixel from where it should be. This is also called the brighter, fatter effect. And then, in the general case, we've also got improvements to the ramp fitting algorithm. This is due to a fellow named Tim Brand, who's at the Space Telescope. It's available in the pipeline, but it's not the default for the automatic processing. But I've got this reference here for PSP a couple of years ago where he presents this method and shows how it improves the actual ramp fitting to give you more accurate results. My work is still ongoing on a number of these things, and we keep trying to do better. Going on to imaging mode, which in some sense is the simplest of our modes. We put in our filters, look at the sky. The calibration of this is a well-known thing. We've had various upgrades and improvements since commissioning. We have done a photometric calibration update, in fact, a few of them, most recently in December of last year. This also applies to the ME imaging mode as well, since they're done together. We have worked hard to get our mosaics into better shape when you combine different pointings into a overall image of a field, including by aligning to Gaia DR3, as well as we've got improvements to the guider catalog. So that's not actually NIRSpec, but it's important in figuring out where we're pointing when we're taking our images and updating our world coordinate system. We've got work that has been done on the nearest to guider alignment so that our blind pointing accuracy has been improved. It's actually quite good now. And the charge migration that I mentioned in the last slide is a particular concern for things like point sources where you have a bright core and wings that are not as bright, and this charge migration will move charge from the core to the wings, especially when you're undersampled. So correcting for that becomes important when you're doing your photometry. So all these improvements have been worked on for a few years now. We've also, as I mentioned, been devoting work to the cosmic ray events. And in imaging, there's a bunch of residuals that we can see from these events in the images that we've been working hard to remove, especially because one of the main science cases is deep field observations and science involving faint sources in general. And it turns out that a lot of this work we've done for imaging also gets applied into the dispersed images for the wide field spectroscopy mode. So almost always we do it first in imaging and then try to adapt it for the dispersed image case, which is a little more complicated. Okay. We're still working on some aspects of our imaging calibrations. We have, for example, flat fielding, which we did in commissioning, and we've been having a long, slow process of taking flat fields on the zodiacal background on the sky. This takes a long time because that background is not very bright. So we knew at the start we'd have to take more than 200 hours of on-sky calibrations to try to improve this, and that's a lot of time. And we've been doing 30 or 40 hours per cycle, and you can tell that it takes 4 or 5 cycles to get our calibrations done. So we're now coming to the point where we want to put this into the pipeline and make improvements at the few percent level on the the shape of our flat fields. And we've also been monitoring the NIRSS imaging sensitivity as a function of time. And as was mentioned for NIRSpec, we're actually seeing a slow decline, which is probably degradation of the detectors primarily. It's around the level of 0.1% per year for this one filter that we use for the monitoring. It seems to be a bit different for the other filters where we have less data. And so if you multiply this by 5 years, we're at something like the 0.5% level of change. And at this point, we're going to have to think about putting it into the pipeline, because if we keep going at this rate for, say, another 5 years, it's going to get to the point where this is important for accurate calibration of any individual observation. Here's an example of an image that we took in the program early on, and this shows you the low-level structure in the image. So what I've done in this display is to take this color bar for values near the background. So all the sources which are brighter are just above the top, and we're not worried about them. So this is what the image looked like in an early version of the pipeline, and there were some residual things that we knew were detector effects or other things, like this thing here where you've got this little blue patch. That's actually a problem on the detector called crosshatching, which is a physical defect in the detector. It's not being taken out properly. There's also a region here where things look like you've got an outline around a region there. That's called an epoxy void. So this is, again, a known thing on our detector. And we've got striping along the y-axis, which is this 1/f noise. So that was the pipeline early on in cycle 1. And if we do the same thing now, in a recent version of the pipeline, you see some of these things have been improved. Of course, there's still some residuals, but things are much better, and our calibration in general has improved. There's also, by the way, a little thing here that you see disappears between the two versions, which is something on our pickoff mirror, the mirror that reflects light into NIRSS from the telescope, that had to be revised in our calibrations and remove it because it was there in every image. So we've made improvements in that kind of thing as well. So, we still have residuals, but things are getting better with time. And if you're looking at faint sources, of course, all this is important. I mentioned these snowballs, this large particle events on the detector, and I'll just show you an example because these are particularly troublesome. They're happening all the time since we're on orbit, or if there's a solar storm, it gets worse. But here's a measurement where we take the first two groups of a ramp and just take the difference to get a measurement of the signal. So this is the first measurement we can make in this observation between two of the groups, group 2 minus group 1. And you see, in fact, here is an actual faint object in the field. This is a little galaxy that happens to be here, which I picked because it was there. These things here are bad pixels. Don't worry about those. This is raw data, and we haven't corrected for them yet. But if we look at then the next group, we get a snowball, which is this large dumping of charge over about a radius of 6 or 7 pixels, so it's almost circular. And a lot of charge is put onto these pixels. I estimate something like 4.5 million electrons are dumped on this circle here, and it saturates all these pixels, so you don't get any more data for them. But also this charge, which is dumped here, with this charge migration, tends to move out from this circle here in all directions. And therefore, when you look at the rate image that is produced for this with no correction, you get this circular halo, which is the charge that was in that snowball at the center here, which is moved outward. and gets picked up because it's not corrected for in the pipeline in this version, which is early on. And obviously, if you're measuring this galaxy here, you've got a problem with this halo of signal coming in that's not real. It's from the cosmic ray event, and you want to remove it. In the middle here, our automatic jump detection in the pipeline finds that there's a jump and moves it, and you get a good result, but it gets out here. It's below the threshold. If you know there's a snowball, you can then go and look for this and remove it. So they did put stuff in the pipeline for this. And again, in a recent version of the pipeline, we have removed all this nasty stuff that you don't want for your faint objects, and you'd get a nice, clean measurement of this particular galaxy here in the field if you're interested in it, which of course this particular program was, because it was a faint objects deep field kind of program. So this has been done, and we're still working on improving the details in some edge cases, but these things are happening all the time, and we've made big improvements in allowing for them and getting rid of them. Another thing that we have done, as I mentioned, was align images to Gaia DR3. Here's a case where our observation in a crowded field probably found the wrong guide star. And the guide star that we think we're guiding on was not the star we were actually guiding on. So the position that was sent from the telescope and saying this is where our pointing was off. You see the field and all these stars, and these white circles are where the Gaia stars are supposed to be in this image, if we believe our world coordinate system, and you can see they're all offset like from here to here. This is about a 0.7 second offset, and it's systematic. It's because our coordinates are simply wrong. Again, as I said, presumably because we're mistaken about exactly what source we were guiding on. This was an early version of the pipeline, and then in the current version, we now have the Gaia stars right on top of the actual stars, and this is because we have corrected our world coordinate system, and we're reporting more accurate positions. So we can still occasionally get offsets, and we don't align perfectly, but the majority of the time we get things in imaging aligned really nicely, and all the coordinates are what they should be, which of course is a good thing. That's the end for imaging. We'll talk about the aperture masking interferometry next. I'm not as an expert on this, though I do some of the calibration. This is a case where we put a mask into the beam with apertures, and there's interferometry between the different apertures in this mask. So you get an interferometric image of your field, and you have to then reduce it with interferometric kind of algorithms to get information about very fine scale structure in your field of view. And so you do better than you would in regular imaging by a factor of a few in your angular resolution, your PSF core resolution. So there's been many changes to this since cycle 1 as they've been working on the data on sky. One of the things that's important to know when you do this reduction is exactly what your mask geometry is. And that has been improved by analysis in detail of the on-sky data. And they've been trying hard to improve the so-called level 3 analysis, where they actually try to do the interferometric analysis and give you interferometric quantities like closure phases. And so the output products have now been put in this specific interferometry fits format because it's interferometric data. So this is the only part of the pipeline that uses this format. And we are providing closure phases between the different mask apertures and also amplitudes between them, which you would not normally use on the ground because the atmosphere messes that up. But because we're out in space and we're stable, you get the amplitudes, which is another way to look at how good your data reduction is. And they have put in change in the last year or so that we use ramp by ramp analysis, because you usually take many, many different short ramps to get your interferometric data. But by using the individual ramps, we can actually derive the uncertainties in these interferometric values directly from the distribution of measurements, and this gives you a more accurate error analysis. So all of this is in the pipeline now. The upshot of this is that with all these changes and improvements in our reduction algorithms, we've improved the sensitivity to faint objects right beside bright objects by about a factor of 2 at most separations since cycle 1. We also did an update to the so-called SciAF, the Science Instrument Aperture file, which was mentioned with NIRSpec, which tells you where you're pointing and gets things in the right place in your field of view, to try to put the star in exactly the same pixel for different filters, because there is a small filter-to-filter wedge offset between our different NIRISS filters that we see in imaging. And normally we don't worry about it because we just allow for it in the world coordinate system. But for this particular purpose, we would like to actually correct for that and put the star peak right on the same pixel with as much accuracy as we can. So they've done that, which helps with the analysis. And then there's a mode that's particularly vulnerable to charge migration, so they put in a correction for that to try to eliminate data that's above the point where too much charge migration occurs, which improves the results you get out of the ME analysis. And just to show some brief accurate results, this is from an early observation we did of a binary star, AB Dor, which has a third star right beside it, which is much fainter. And we use this to try to see how faint we can go. So the y-axis is how many magnitudes fainter you can go and detect something with respect to your bright star in the field. We're talking about 7 or 8 magnitudes in the best case, so factors of 100 or 1,000. No, sorry. Yes, sorry, hundreds or 1,000. These are 2 different calibrators being used to tell you what a single star looks like. A couple of these are having problems, so we'll not worry about them. But generally speaking, these different curves are showing you how things have changed with time, to the black curve, which is the latest, and the blue curve. And it was the original case in commissioning, and they have all come down, sometimes more at larger separations than smaller ones, but this kind of improvement by a magnitude or so is make it easier to detect the exoplanets that we're trying to directly image in this mode. This mode has been somewhat underutilized, but hopefully with these data reduction improvements, people will get back to using it more. Going on to wide field slitless, which is one of our major modes and one which we've had some of the most dramatic improvements on. This is the mode where we put in a grism in the beam, and every object in the field produces a spectrum. But of course, because you don't have slits or anything, this makes it complicated if you've got lots of stuff visible in your field. So we've been working hard on this for a few years. We've made significant improvements in the trace and wavelength calibration, because in commissioning we had only limited data, and we've gotten a lot more since then to work with. We've got in the pipeline a profile fitting bad pixel replacement step, the so-called pixel replace step, which is not on by default for NIRISS, but you can turn it on and it actually produces an improvement in our data. This was actually originally invented for MIRI, but it works perfectly well for us as well. We've had various changes to the photometric calibration, which was updated in January of this year. And more recently, we've tried to allow for the dispersion changes across the field. So we have a position-dependent photometric calibration. This is a pretty small correction for NIRISS, but it's been active in the next release, which is actually the one that was done about a week ago, April 16th. It should be active now, I believe. Something still in development is contamination corrections, which is a lot of work. There's many issues involved for this, and we're still trying to get this to be in good shape. It's going to take a while yet. Just to show you what our data looks like for this mode, here's a direct image of a particular star field. It's not too crowded, but excuse me, I had a pop-up which is from PowerPoint, which I didn't expect, but it's not relevant. This is the image of a field that we're observed in this mode. This is what the direct image looks like, but when you put in the GRISM, you get all these spectra, multiple orders. So, for example, here's one source. We get a direct image analog. It's order 0. We get order 1, order 2, very faintly order 3, order -1. We're only calibrating order 1, and in one case order 2 for one filter, but all this other stuff is there, and these can contaminate the order 0 spectra that we want, but also we need to calibrate how these spectra change in position and their wavelengths at different positions in the field. So it can get complicated, but this field is not really crowded. If you look at a more crowded field, you get this, and now you can see spectra everywhere. It's very hard to deal with this without correcting for contamination. And if I zoom in to some part of this field, for example, here's an order 1 spectrum, the one that we want to extract, and it's reasonably isolated, but then down here there's one of a different source, and it's right on top of an order 2 spectrum from a different star. So we really need to decontaminate some of these spectra to get a good extraction and get a good calibration. And this is a lot of work, especially when all sorts of stuff is going on in the field like this. So this is the kind of problem we're facing, depending on what field you're looking at. We had in commissioning a trace solution, and we've been working to improve that. Here's an example from one of these observations. You see first the cutout of a spectrum, which is being used to measure the trace. The cyan points are the predicted trace center from the original commissioning calibration, and you can see it's not really in the right place. The black points are the actual measured centroids, and they're almost hidden by the magenta points, which is the revised solution. So it was off by a pixel or a pixel and a half originally, and then when we have done more work, we've got things to be very close, which is, of course, what you want, so you extract the right spectrum. How big this offset is dependent on where you were in the field and what filter and so on. And then in order 2, the situation was worse. So this is the same object. This is order 2 in the same observation. The commissioning calibration then was like this. So you see it has much more curvature than it should. The background spectrum is not very much curved. It's slightly tilted up, but the fit was not great, and so you get larger offsets, and they're dependent on wavelength, which is going from right to left in the spectrum. And that was the original, and now you see in magenta, again on top of the black, the new predicted centroids, and they're very much better in precision. So this is a big improvement in what you get out of the pipeline, because this is what they use to say, where do I extract my spectrum? And another graphic of this solution improvement is showing the overall situation for one particular combination of GRISM and filter. The purple was all the measurements we had in the fit originally in commissioning. You saw a lot of scatter in the residuals, and it wasn't centered near zero. The average is over here, about a pixel off. See, we were having trouble with our solution and the measurements at that time, and the most recent case is this green histogram. And you see now we're in good shape. It's not only centered on zero, which we want, it's also quite tight. And the dispersion, or the standard deviation, if you would rather, is about a 20th of a pixel, which is pretty good. That's about as much as you can expect in this kind of case. We're measuring a bunch of sources in different places in the field. So this has been a big improvement in our data products from the result of this calibration. You got the same thing for wavelength. We measure wavelengths in a planetary nebula across the field and try to fit it. So this is what we had in commissioning. The individual stars are for different mosaic points. We had a 3x3 mosaic across the detector. The dashed dot is the average, and then the gray is one standard deviation. So you see we had a fair amount of dispersion in terms of pixels. Plus or minus 1 sigma is 1.8 pixels. That's not good. And the mean is not quite zero for that GRISM. For the other one, it's slightly better sigma. It's only 1.1 pixels, but the mean is actually more offset. So that's what we had in our initial crude calibration. And this is what we have now from December 2023 calibration. And you see the points are all tightly grouped by comparison, and now our mean is close to 0 pixels, and the 1 sigma is about 1/4 of a pixel, depending on which of the two GRISMs. So this is much better than it was before, and hence the wavelength calibration is much improved. In terms of photometry, we also had significant improvements. Here's the results of an observation of a photometric standard star. The blue spectrum here is what we have in CalSpec, our calibration web page for HST and JWST. That's what we were supposed to get. And these scattered points all over the place are what we actually extracted in commissioning. And you can see there's not only large offsets, but they tend to be systematic. Some of these curves are up, and some of them are having problems in part of the spectral range and not as bad in others. So this is not good. It's 10% uncertainties kind of thing. That was the result right at the start of cycle 1. We have improved things, and this is the current situation on that same observation for the same star. I wasn't consistent. I plotted the spectrum in red here, but now the points behind it are the measurements that we get out of the pipeline. And you can see we are starting to resolve some of these hydrogen absorption lines in the spectrum, and overall the tightness of these values around the expected result is much better. And don't worry about the edges. This is where we have low signal and noise just gets amplified. But in the middle here, which is the scientifically important part of the spectrum, we're getting a much better result than within maybe a couple of percent instead of plus or minus 5 or 10%. So that's the end of the description of wide field slitless. We could show more about the contamination, but that's a bit too crude. Work ongoing. So going to our final mode, the SOS mode, another popular mode for exoplanet transit. We've had a lot of work done on this, similarly to the things we've done for the wide field slitless case, because we've got the same kind of calibrations we want to do. The photometric calibration has been updated most recently last December, so only a few months ago. And as was the case with wide field slitless, we needed to work to improve the trace solution and the wavelength solution. In this case, it's a little easier than the Why it's slitless? Because the spectra are always in almost the same place. But on the other hand, our data is a little different. So we've made improvements in those cases. And then something we didn't expect we had to do was to make a lot of work on the background subtraction for this mode, because we thought it would be simple. And it turned out when we got actual on-sky data that it wasn't quite as simple as we had intended, or had predicted, I should say. So those have been things we've been working on for a few years. This is what the spectra look like when you take a spectrum in this mode, just to show you. We've got several spectral orders on our detector. The first order is the one at the bottom, so that covers most of the wavelength range. Then order 2 is up above it and covers the short wavelength range from about 0.8 to 0.6 microns. And in this case, you can actually see, if you have good screen resolution, H alpha is here. So then you have more lines around 1 micron because it's an A-type star. We also have order 3 here. You've got minimum in these higher orders because of the blaze of the grism. So this is in order 2, the signal just about goes down to 0. But that's redundant with order 1, so we don't care. There's also a very faint order 4 up there, which we don't bother to try to deal with. We had to work on our trace because we found out, and this was expected, that each time we put the grism into the beam, we get a slightly different position for our spectrum. So this is the right-hand side of the spectrum in the previous image, and here's 2 observations of the same star in a program. And you see that the position of the trace moves by a few pixels, about 5 or 6 pixels. This is a small rotation because the grism is slightly rotated in the wheel when we put it in, because of the limitations of how accurately we control the step of the wheel when we put the grism in. So we have work to get this all calibrated, and so it's all done. We have a way to trace this from the data that we get from the telescope and make an accurate trace solution that follows these small rotations and gives you a nice, consistent extraction of the spectrum. I also mentioned the background, so here's an example of the background where I'm showing the spectrum. And if you look at the faint part, you've got a discontinuity in your background here. And this is because we're dispersing different orders onto the science array here from the field of view on the sky. And on the right-hand side, we are seeing order 0, order 1, and order 2. On the left-hand side, we're seeing only orders 1 and 2. And order 0 happens to be nice and bright, and so you get a discontinuity where you reach the edge of the pickoff mirror for order 0, and it no longer contributes. And because we knew this was here, what we found is that this shape varies a little bit from pointing to pointing in the sky, which we didn't expect when we were in commissioning. We had to take a lot of work to try to calibrate that and find a good automatic way in the pipeline to take this out. We have done that, and so when you do the background subtraction, it becomes this. And the point is, you can see this whole structure here is completely gone to a pretty good degree of accuracy. And then you can extract the spectra, and you don't get a background contamination in. In terms of the science data, here's an example of an exoplanet observation showing the improvement you get with this background subtraction being done. On the left was an earlier version where there was no background subtraction. We're plotting the derived radius of the planet to the radius of the star from the eclipse depth. This is a large Jupiter-like planet close to a late type main sequence star, so the ratio is around 14%. But this is known from other observations, including with NIRSpec, I think, to be flat with wavelength, but we weren't getting that out of our analysis. We were getting a change with wavelength, and this was because of the background contamination. And then on the right is what we get with the background subtraction being done, and now you see it's nice and flat. And so we have taken out this systematic effect that the background was putting into the data. We've got other things that are either currently in the latest release or are coming. So we've got a very large speed increase for the time series reductions. This is purely a pipeline thing and not a calibration on sky type thing. But for example, this process reduces a particular test case from 16 hours down to 32 minutes. Pretty enormous factor. And then there's a technical report in preparation. Tim Brand, who I mentioned earlier, is also responsible for this in large part. And we are doing this 1RF noise corrections in a specific way that does better for this particular kind of observation, which I will now show you. So here's an example of what the images look like. On the bottom, here's what we get with no 1RF removal. And then we apply our algorithm and all this striping in the y-axis, which is the noise from the amplifiers is removed, and you get a much better image up here. And this actually has practical implications for the analysis. It's not just cosmetic. So here is the light curve spectrum that you get, or light curve time series you get from this observation. This is what you get in the standard pipeline without this 1/f correction. We can see the eclipse in order 1. We don't see it in order 2. It's too noisy, and it's expected to be smaller because the wavelength is different. But when we put in this 1/f noise removal, it's a dramatic improvement in the signal to noise, and now we get a much better result for order 1 and also for order 2, and we can then actually see the eclipse as compared to what it was over here where it was too noisy. So this is a significant improvement for the exoplanet people. We're also thinking of work in the future to, for example, use an empirical PSF instead of the simulated ones, because there's some wings in our PSFs that are not in the simulations, and this should improve our overlap corrections. And there's a small tilt of our monochromatic PSF. It's not right along the Y pixel axis. It's tilted by something like 1 degree, which has not been used in the past, but now we're going to put it in, and it will also make some improvement in the way the spectra come out. So finally, I want to mention that we also have a new mode. It's the first time we've done this for NIRISS. For this particular kind of observation is to use this multi-stripe mode of reading that was mentioned for NIRSpec. To allow you to go brighter. In our case, we can go about 4 magnitudes brighter at the bright end with this different readout pattern if it works as expected. We're going to try to start working with it in June and July, and we certainly hope it will work as expected, and we'll get access to some of the brighter and well-known exoplanets that people want to observe with JWebbinar. Several Cycle 5 programs are asking to use this new mode for that purpose.